Hi everyone, thanks for the opportunity to talk in this meeting. I will talk here on singularities in cosmological manifolds, in which I will try to highlight some of the main mathematical challenges today. In fact, this is a vast and complicated subject, so I will speak only from the perspective of inhomogeneous cosmology. As you must know, one of the major problems of cosmological models is the condition that universe evolution starts from a point-like singularity. From the point from the point of view of physics, it's an object that cannot exist. Let's, before the hardcore, try to introduce the problem in the simplest way. In cosmology, this is the density dynamic equation for a homogeneous space-time metric, where P is the pressure and A is the scale factor. A dot over A is the Hubble space expansion rate, and K over A square is the space curvature in any time slice of the universe. It's proportional to the Ricci scalar curvature. Well, we see that the energy density, and in general also both pressure and Gaussian curvature, becomes singular for A equals to 0. That is, energy density becomes an infinity value in T equals 0. This is what we call Friedmann singularity, a point-like cosmological singularity that, in terms of physics, we need to avoid. Thus, the evolution of the scale factor determines how the expansion rate of the universe behaves, and it works quite good if we compare to the experiments. The red here describes how the inhomogeneous cosmology avoiding point-like singularities works. And the blue, we have the homogeneous cosmology, which allows us to determine that the current age of the universe is about 40 billion years since the Big Bang. Redshift 0 is the universe today. And two examples of inhomogeneous cosmologies are the bouncy and the cusp-like models. In a more technical sense, we will talk about the singularity problems in inhomogeneous cosmology. And to achieve this goal, the outline of this talk is split into those four subjects. Well, let's start from physics, involve the concept of Friedmann singularity. This is the most usual metric that results the standard model of cosmology. Okay, this is the Friedmann-Lemaitre Robertson-Walker metric, and from that we can get the lambda CDM, a cold dark matter in expansion given by lambda, the cosmological constant, which can be interpreted as dark energy. The lambda CDM is the scientific paradigm which explains the evolution of the universe from a singularity where the Big Bang happens and the universe born. Here, S is space, T is time, A, as I said, is the scale factor that governs the cosmological expansion, and sigma is a connected 3D Riemannian manifold of constant curvature endowed of the warped product with a given manifold, which is the space-time. From this metric, we compute Christoffel symbols, then the Ricci tensor, and adding the stress energy tensor, okay, for a perfect fluid, which is in the Einstein field equations. We substitute them in the Einstein field equations to obtain the Friedmann ones. The one in the green is called acceleration Friedmann equation. From these two equations, then we derive the Hubble parameter, which is a measure of the expansion rate of the universe because it contains the main ingredients of the problem. The gravitational constant, speed of light, energy density, curvature, and scale factor. By the way, this is the Einstein field equations that you know. The left is for geometry and right for energy, and G min E is the metric tensor. Okay, the big question here is how can this model be tested from the observations, okay? The density parameter omega has been defined as the ratio between the average density to the critical density. The critical density is the density at which the universe would stop expanding only after an infinite time. Critical density is really derived from Friedmann equations. The observational constraints equation can then be given, comparing the measurements from the universe today. 0 here is for redshift equals to 0. And it comes from different sources of energy density. From radiation, from dark matter, space curvature, and dark energy. Deriving critical density and measuring mainly those densities from very sophisticated observational experiments. Okay, mainly the ones that can get the density of dark energy and dark matter. The input-output works like this. Okay, we have those matter here, and it goes to the model to plot this variable, okay, against time. So that's the output from different models inputs, expansion rate as a function of time. Note that the red model here indicates that lambda CDM is the current paradigm of cosmology. That is, the universe contains about 30% of dark matter and 70% of dark energy. Well, but behind all this approach, what is the biggest problem for mathematicians? I believe that you are already suspicious of this singularity that appears here. Okay, let's find out this. Well, the major problem for singularities in space-time in matrix is the existence of a non-zero congruence factor that appears in the exact solution of the field equations. This happens when a field of expanding velocities of a return, we say contraction, the inverse of this theta, is calculated on the geodesic. The end result always is a line element composed of a point and its projection. This phenomenon was already observed in quantum mechanics in the late 70s. It was called bits of matter or quantum slits. This is very important for to define the line element in Lagrangians. And in the case of Einstein equations, this problem is addressed through the Landau-Raychaudhuri equation, which I'm not going to detail here. Its solution says that the contraction coefficient, the inverse of theta, is greater than or equal to the congruence factor, even when this term, that's equivalent to the Friedmann singularity, is null. Therefore, the exact solution of Einstein equation is incompatible with Friedmann singularity. Its proof is known as focusing theorem, on which I'm not going to detail here, but this is the important result actually in red. But the question is how to solve this problem in cosmology. Firstly, the answer comes from a geometric interpretation based on singular semi-Riemannian manifolds. So where are the simplest solutions from where we start? Solutions from topology. In this paper, Stoica's paper, it's properly show that appropriate interpretation of what mean topological and distance separations are. The statement is the following. From a family of manifolds which are homeomorphic with a given geometric surface, we can take a metric that makes it look like a surface with a singularity. Well, then, on a manifold which is homeomorphic with a cylinder, for example, one can take a metric that makes it look like a cone. Note that the cone's vertex is actually a circle of the cylinder, and then the metric is degenerate on this cycle. Similarly, one should not assume that at the Big Bang singularity, the entire space was a point-like object, but only the space metric was degenerated at t equals to 0. As I said before, the trivial dynamical solutions are the bouncing models. Fine. The theoretical basis of such models is based on the so-called BKL conjecture introduced by Belinsky, Kalanetnikov, and Lifshitz, Russian physicists. It says that close to a singularity, the variation of the gravitational field from one location to the next changes over time as a nonlinear oscillator, ordinary differential equation actually, and therefore the variety always has a non-zero congruence factor whose nodes can expand. These models, including the mixed master introduced by Charles Misner, are based on 3D Lie algebras classified according to the Bianchi type. Mainly types are type 8 and type 9. Type 9 is the orthogonal group, as you know. And it's important to say that with the hypothesis of quantum here, this sector, quantum gravity, this conjecture is well established. We will talk about quantum gravity later. As bouncing models can present numerous mathematical problems, Gaussian curvature for instance, and physical inconsistencies from its thermodynamics, for example, another class of non-homogeneous cosmology, which is not bouncing, has recently been introduced and has been called Cusp Cosmology. Both approaches are suitable for Friedman singularity free topologies. Okay. Again, quantum gravity is necessary for all those inhomogeneous-like approaches, and the tori is the usual surface related to the Stoichkos approach presented here. Okay, before we go to Cusp, let's point out the main boundary limitation. In general, there is a difficulty in mapping the BKL nonlinearities of the tracers, as we see here, okay, with necessary and explicit geometry that allow it to determine the Gaussian curvature. Here, the nonlinear of the tracers are only rotation, for example, but as you can see from mixed master simulations, it gets very complicated, and this becomes even more crucial when the topological deformations distort the matrix and act as matter. That is, producing a gravitational effect from topological defects and not from the stellar mass. In this case, the weight of the energy density component from the curvature can be very high and should be considered explicitly as an observational constraint. So we can say that the main problem in this approach is how to compute the Gaussian curvature as a function of the redshift. We still don't know. An alternative that allows both mathematics and physics to move forward with greater consistency starts, in my view, from the so-called Cusp Cosmology, where two main cosmological sectors are considered, pre-Big Bang and Big Bang sector. In the pre-Big Bang, we have the Singularity sector without quantum gravity. In the Big Bang sector, we have the quantum sector that depends on a very special physical approach, including string theory, because we need two more dimensions from string theory, so we call two branes here. And then we go to the baryonic sector, which is totally compatible with the lambda CDM model. So we have three sectors here, sigma tau, sigma q, and sigma t. Well, we have no time to show here, but let's consider that due to a wave instability like this, it's possible to show that the quantum sector may naturally arises. Take into account the theory of tachyons. as particles whose steady state has infinite energy and can decay into photons. The pre-Big Bang cusp scenario constructed based on the following conjecture. Suppose phi is an infinite metric of zero curvature and non-zero energy density. It goes to infinity actually, whose symmetry around the tachyonic condensation is broken and then oscillates in a tachyonic temporal direction. So there is a hyperbolic matrix that by a tautochrone field action will be collapsed into a 4D quantum sector. So this is the sigma tau, which is collapsed going to the tau q. From the accumulation of energy in sigma q, the sigma t structure emerges, which expands according to the injection of energy from sigma tau. Note that in this scenario, free of point-like singularity, the dark energy comes from sigma tau, and at least part of the dark matter can be explained by topological deformation due to the distortion imposed by the link between sigma tau and sigma t. One of the approaches to Cusp Cosmology comes from studying its projected geometry, which is based on the metric called conchoid of Nicomedes, which has the general shape like this. In the cosmological projection, we use the surfaces of a revolution given by this family, that for a given value of n, where, for example, for n equals to 4, can be parameterized like this. From that, we can compute using, for example, Martian-Kubi's algorithm, the quantic surface of a revolution. So that's our projection for the Cusp Cosmology. A metric like this can be made compatible with the so-called Lemaitre-Thomann-Bond BKL cosmology when we have a quantum sector. We have no time to discuss this in this talk, but please see this recent paper for more details. Okay, Bourgeois 2019. In this case, the scale factor and critical density also depend on the density of the quantum gravity sector that evolves over time. Therefore, the scale factor changes for each chosen node as well as the Gaussian curvature. For a given n in Cusp Cosmology, we can compute the Gaussian curvature as a function of the redshift. This is currently the strongest argument for testing Cusp Cosmology. So we see that even if the curvature of the baryonic sector is closed, the expansion makes the universe locally flat, which is absolutely compatible with the observations and also with inflationary assumptions, which are very common in cosmology. Another important consideration is still to be investigated, is to prove that the gravitational force field created by the curvature of sigma tau follows a tautochrone action, what is foreseen and also essential in the Cusp Cosmology conjecture. In this figure, we highlight the need for quantum gravity, whose discrete feature of operation is very similar to that of a sponge soaked in a water. Okay, as you know, as long as its volume is not filled, it's attracting water. After filling it, it repels water, so the force becomes repulsive. And quantum gravity works like this. Okay. Here we see two configurations for the projection with two spatial dimensions. On the left surface, the revolution with n equals 2, the cubic one, and the quintic one on the right. Okay, what's still open in the Cusp Cosmology? Okay, besides this tautochrone proof. Okay, if it's proved that the action of the cusp fields follows a tautochrone of a revolution, we will in fact have a new cosmology at hand. I say that because the tautochrone has both Hamiltonian and Lagrangian that are well known, and this is the first ingredient we need for constructing a consistent cosmological model. But in this context, which we usually call topological cosmology from Hamiltonian and Lagrangian, it's necessary to identify the fundamental domains and their identifications as closure and orientation. And then, from manifolds already know, like tori, for example, we start to assemble a dynamical a manifold that includes the matrix of the three sectors along the scale factor variation. I mean, we can do that by gluing different hypersurfaces, and this is crucial for us, okay, to go beyond the cosmology of projection. From a technical point of view, we then have the 3D manifold that can be divided into three hypersurfaces, glued from a topological point of view, that results from an evolution over a tachyonic time that changes to a photonic time due to the quantum confinement of the primordial energy flow. The work involving toroidal forms has been developed into the context of fiber and hyperbolic space. This is the first mathematical challenge to try to generate a consistent and effective Cusp cosmology theory. In this paper here, whose content is too dense for this talk, and maybe it deserves a complementary talk, let's see, in the future, for this community. But in this paper, the Cusp cosmology is built using Seifert fiber spaces. This starting point is the Thurston's geometry that teaches us how to do a topological surgery on a manifold. It means a manifold is scattered along essential spheres and tori. A connected component of the result of this process is considered, completing spheres with balls and adding the torus at infinity, in order to obtain the so-called the end of the manifold. This is, and we needed some definition how to produce the cusp from this elementary geometry. So we use this cube. So the definition of a cusp is like this, into the elementary cube and 2D torus homeomorphism. Note that we need the 2D torus as we need to glue the boundary to a torus with SF spheres. This is the elementary 6 tetrahedra cube Z for the cusp hyperspace triangulation. And here is the first two glued cubes as the next elementary example. But here note that C has its vertices at infinity. And then we have the fiber cusp hyperspace. Of course, for the people that works in this area, the assembly topological evolution can be obtained. Okay, the assembly topological evolution can be obtained from the elementary manifold M by using splice diagrams. I'm not going to detail here, we don't need that now. But in short, we can say that the Cusp cosmology has been constructed taking the 3D hyperbolic space, which is the upper half of Euclidean space with this matrix. And this infinite cusp construction can have a finite volume, which is compatible to the Big Bang cosmological constraints. Okay. Finally, in my concluding remarks, I would like to point out some of the main challenges in this framework. First challenge concerns to how to insert quantum gravity in homogeneous models, that is, how much we depend on algebraic and topological tools to glue a quantum high surface in the traditional matrix for the lambda CDM. Or I can say, what is the topological variety that in S3 generates an appropriate metric for quantum cosmology? That's the big challenge. Another great challenge from this to come is how to compute the homotopy groups of the quantum gravity manifolds. Okay, so the second challenge is the following. How to estimate Gaussian curvatures as a function of redshift in bouncing models. Okay, we are in the right way for the Cusp Cosmology, but in the bouncing it's still a big challenge. The third one concerns to how to calculate the energy density from deformations and topological defects in the space-time curvature. I remind you that in such case, dark matter density can mimic topological deformations, distortions, or defects. So they have, the same hole here. And the last challenge for today is a geometric one. I would say that it is still necessary to prove, as I said before, that the curvatures in the Cusp model with tachyonic-like spacetime are tautochrones of revolution. Finally, I would like to say that analyzing the sophisticated mathematical apparatus that we have today in face of the new demands of cosmology, especially related to the theory of singularities, it's time to promote the approximation of mathematical topology and cosmology as never before. Well, that's all. Thanks to Dan, my team in this research, and thank you very much. I appreciate your attention, and please send me comments or questions about this talk.